Okay, we're going to talk about correlation for a few minutes. And this is going to be the only technical quantitative material in this lecture. You don't have to memorize all these quantitative details, but I'm going to try to explain to you what kind of a measurement correlation is and what it represents, because it's pretty important to understand correlations if you're going to be able to understand any kind of research in the human domain. Okay? So correlation is a kind of relationship between two properties or two sets of measurements, x and y. What does it mean? Well, if they correlate, then it means that particular differences between entities in property x tend to coincide with particular differences in property y. Those entities might be people, they might be words, they might be I don't even know, different locations in time or space. It can be just about anything. So it's just differences in property X between things tend to coincide with specific differences in property Y also, to a greater extent than we would expect by chance if X and Y weren't related. And that second part there, greater than we would expect by chance if they were unrelated, that's basically the foundation of almost all statistical modeling that you see in experimental work is comparing the actual data that we observed to what we would expect by chance if there was no relationship between the things we were studying. It's not super important how that works quantitatively, but conceptually, that's what most statistical tests are doing. Now, here's an example that is illustrating poorly how correlation works. I'm going to give you a better example in the next slide. This is from a statistics textbook. And there's some silly example here about how many, packets of junk mail each person received and how many advertisements were in each. This guy's Australian, so he calls them adverts. But yeah, that's what this is about. And so there's just 6 people here. They're not ordered in any particular order. They're just assigned numbers, more or less randomly. And you're seeing for each person, here's how many packages they received, and here's how many advertisements were in the package. Here, here, so on and so forth. And so the observation here is that, well, across all of these people, I guess there's only 5 of them, even though it's labeled up to 6, there's an average number of advertisements they got, an average number of packages they got, and these are represented by the horizontal lines for each measurement. This is the advertising measure, here's the mean, the average. This is the package measure, here's the mean, or the average. And if we want to know whether people who differ in the amount of packages they got also differ in the amount of advertisements that they got, we can compare each of these measurements to the mean across the entire group. So person 1 here got a lower than average number of packets, that's shown by this downgoing line from the average. They also got a slightly lower than average number of advertisements. Similarly, person 2, lower than average number of packets, lower than average number of advertisements. Person 5, greater than average number of packets, and also, hey, look, they got a greater than average number of advertisements too. So this is a graph, I mean, it has very few data points, but it's just illustrating the point that you could use variation in this measurement to predict variation in this one, or vice versa, because these two sets of measurements seem to be related to one another. In particular, people who score greater than average on one measurement tend to score greater than average on the other one as well. If these were not related, then you wouldn't expect that. You could look over at subject 2 and see that that person had a lower than average number of packets, and it might be equally likely that they have a higher than average or lower than average number of advertisements. But that's not what we see in this graph. Instead, it looks like these differences are pretty reliably related to one another. And that kind of relationship that we're seeing here is a positive correlation. It means that, in general, the two measurements tend to go in the same direction, right? Okay, so that's illustrating correlation. This is not a great way of looking at correlations visually, and there's a much more common method of doing this, which is the scatter plot. So here is a scatter plot. Scatter plot is any kind of a visual display that takes your data points. So each of these represents one data point, and it plots one of your variables of interest on the horizontal axis and one of your variables of interest on the vertical axis. That's what a scatter plot is. And this allows you to see quite clearly whether and how the two variables are related. So if they weren't related, I'll tell you that this would just look like a blizzard of random dots that would be spread all over the graph. It would be a cloud. That's what two uncorrelated variables look like. What we're seeing here instead, this is another sort of stupid joke example from this textbook where he's talking about how many chapters have you read of my statistics textbook and what is your level of spiritual enrichment, where we're pretending that we can measure spiritual enrichment on this vertical axis here. And the joke is that as you look at the greater number of chapters that people have read, their spiritual enrichment predictably goes down every time they read a new chapter of the statistics textbook. So that's the sort of joke from Field, but it's illustrating a serious point, which is that this relationship is visually really obvious in here. It's clearly a downward sloping diagonal. What that means is that as your x variable gets greater, your y variable is getting smaller. So this is a predictable, clear relationship between these two variables. In this case, it's a negative relationship, so we would call this a negative correlation. Right? If it were a positive correlation, if your levels of spiritual enrichment were going up as you read more chapters of the textbook, the general form of this plot would be a diagonal sloping upwards. This one is negative, so it's sloping downwards. Scatter plots are really useful plots. They're one of the most useful kinds of visualizations that you can do of data. Doesn't require any special technical ability to assess a scatter plot. It's really a nice way of visually making these relationships clear. Now, one slide of technical details. You don't need to be able to reproduce these equations or anything, but I want to describe in a little bit more detail how we actually measure correlation, because it's going to be conceptually super important what correlation is. And so I want the more technically minded amongst you to at least have the possibility of figuring out what that corresponds to quantitatively. So let me try to explain what's going on here. Correlation starts with a measurement that we refer to as covariance. And the covariance between two variables, or between two sets of measurements, really, is going to take on this form, where there's some sort of scary mathematical notation here. Don't worry too much about the scary notation. I'm about to explain it. First of all, this sigma character just means that we're summing up a whole bunch of values over some variables. Right? These variables are the x and y variables, the sets of measurements that we've gathered in some experiment. Let's say it's, again, number of chapters read and spiritual enrichment. So x is number of chapters read, y is spiritual enrichment. This little subscript I just means for any individual data point, right? Any individual thing that we've measured, what is that specific thing's value for this number of chapters variable, whether that's a different person or measuring the same person at a different time, doesn't matter. Here's one measurement of number of chapters read, and this little bar over the variable stands for the average or the mean, right? So this any given observation, compare it to the mean value. Is it greater than the mean or less than the mean? This is exactly what we were doing in the first plot up above, right? And now do the same thing for the other variable, levels of spiritual enrichment for that same observation, right? That same person or that same measurement we took. Compare that to the mean for spiritual enrichment. Is this one greater than the mean or less than the mean? And so this top part here tells you to do that over every single observation that you have in your experiment, or every single data point you have, and sum them all together. And then this n minus 1, first of all, ignore the minus 1. It's not conceptually important. There's a good technical reason why it's there, but it's super confusing. Just pretend that's not there. N stands for the total number of data points in your data. So what you're actually doing here is adding together all of these things, right, where you're looking at, is x above average? Is y above average? you're going to add all those together and divide them by the total number of data points. So what you're getting is like an average covariance value or correlation value over every single data point in your experiment. That's what the n is for. It's just saying divide by the number of points you have, so you're getting some kind of an average, right? Now, what's going to go on with these measurements? Well, consider, again, the reading chapters in spiritual enrichment example. If people who read an above average number of chapters have below average spiritual enrichment, then this is going to be a positive number times a negative number, and the result will be negative. If people who are below average number of chapters, haven't read much, have higher than average spiritual enrichment, then this is going to be a negative number times a positive number, and it's also going to be negative. And so if there's a general relationship, whereas this one goes up, this one goes down, and vice versa, then we would expect most of these products to be negative numbers because we're multiplying them by each other. When you add them up, you're going to get a giant negative number, and then you're going to divide it by the number of data points you have to get an average, which will also be a negative number. So if you have two variables that are related in this inverse relationship, this is going to be a negative number. Of course, if these are both positive, people with greater than average x have greater than average y, then this is going to be a positive number. People with below average x also have below average y, then this will be a negative times a negative. It will also be a positive number. That means if these are directly related to one another, positively related, you're going to get large positive numbers out. If they're inversely related to one another, you're going to get large negative numbers out. And if they're not related to each other at all, then sometimes things with positive values here will have positive values here, so you'll get positive numbers. But sometimes things with positive values here will get negative values here, and you'll get negative numbers. And when you add them all together, you're going to get something close to zero. So you're not going to have any large positive or large negative numbers. In fact, this is going to be close to zero when you have two unrelated variables. And that's the basic principle that correlation operates on. Now, in order to get the actual correlation statistic that you'll probably see in some papers, so I'm going to take the time to try to explain this, you need to do some standardizing this in terms of units, right? Because right now, all we're doing is taking number of chapters read over here and spiritual enrichment based on some kind of imaginary measurement over here. And so whatever results we get from this operation are not going to be in general units. They're going to be in special weird units of chapters read times spiritual enrichment questionnaire questions or something like that. It's going to be in weird uninterpretable units. The only other complication here is that we want to get these in general standard units. And to do that, we have to do some fancy math over here. So again, I'm going to take 3 minutes and try to explain this. Don't worry if you don't understand the technical details. This is more important than this part. So this is the covariance of x and y. That's what this number is. It's like the average amount that they covary or something like that in the same direction or in opposite directions. In order to get a standardized statistic, the famous one here is the Pearson product moment correlation coefficient, which is often called just the correlation coefficient or just R. You'll see people just refer to this as R. Everybody knows what that means. If they don't say otherwise, they're talking about the Pearson R, right? This is the covariance, which we've just calculated, but it's divided by some standardization units for both variables, for both the x variable and the y variable. In particular, this S stands for the standard deviation of any particular set of data points. And this standard deviation is a particular mathematical way of characterizing the variability of some measurements, right? So these are going to be units of variability, and that makes them totally general, right? Rather than being special units of book chapters and spiritual enrichment surveys, these are now going to be units of variation over those two measurements. And that makes this standard or general in terms of its units. So this is going to be the exact same equation as before, this big summation on the top and the n on the bottom, and forget about the -1. It's not conceptually important and it's confusing. Pretend that we're just dividing it by the number of data points we have. But now we're going to divide this, in other words, multiply the bottom, also by these units of variability across the two variables. And now we're going to be expressing the average extent to which these change in the same or opposite directions as a proportion of the general variability that we see in the two variables. That's what makes this a standardized measurement, right? It's now in units of variability instead of units of book chapters or units of spiritual enrichment. This is how you compute R. People will often report this R statistic when they're reporting results in a paper. So I wanted you to have some idea of what it means. Again, if you don't remember all the little technical details, it's not important, but I just want you to understand where this comes from. So R is a statistic that describes how related two variables are and which direction they're related in, while also correcting for the general variability of each of the two variables. That's what R is for. Because of the way this measurement is set up, it's going to necessarily range from a minimum of -1 to a maximum of 1, right, with 0 right in the middle. And -1 would indicate that there is a perfect inverse relationship between x and y. +1 would indicate that there is a perfect direct relationship between x and y. Excuse me. If you don't have any systematic relationship between x and y, then, as we saw earlier, that covariance statistic will average out to 0, and no matter what the units of variability are, this correlation coefficient R will also be close to 0. So this is what this means. -1 is the strongest possible inverse relationship. 1 is the strongest possible positive relationship, and no relationship whatsoever would be equal to an R of 0. So this is what correlation is looking for. Okay, that's correlation. And so you can see there's both a conceptual side to correlation. It's easy to understand the concept, and also there's a specific mathematical implementation of the concept, which is a little bit more complicated, but that's what correlation is. It's both the conceptual idea and its particular mathematical operationalization. So that's correlation. What's causation? And I've written here, I have no idea. I don't know how to define causation. I'm not sure anybody else does anyway. Excuse me, either. But, maybe philosophers of science would have something to say about that. Here's a rough idea that's probably wrong, but it's the best I can do. We can say that X causes Y if and only if X exerts some direct influence on Y in a way that can't be explained by any other means. Okay, so that's a little my attempt to try to define what causation is. I'm sure there's lots of problems with it. We also all have an intuitive sense of what causation is. And the problem is the following. If X causes Y, then everything else being equal, we'd expect X and Y to be correlated, right? I'm trying to think of an example here. If storm clouds cause rain to fall, then we would expect, if we take measurements out in the world, the presence of storm clouds and the presence of rain will be correlated. But if X correlates with Y, it does not follow that X causes Y. And why is that? Well, imagine we go out in the world, we start with the measurements, and we say, hey, there seems to be a positive correlation between rain clouds and rain. What do we infer from that? Well, we might infer correctly that rain clouds cause rain, or we might infer incorrectly that rain causes rain clouds, and we just don't know when we gather observational data that two things are correlated. We don't know what causes what. And so this is a sort of slogan that you'll hear from scientists a lot. Correlation does not imply causation. Right? If we find that X and Y are correlated, then here's some possibilities. Maybe X causes Y, Or maybe Y causes X. Or maybe there's some other factor, Z, that causes both X and Y, and that makes them correlated. Or maybe X and Y don't even have an indirect causal relationship. Maybe the correlation is just a coincidence. It's not easy to figure out which one of these is the right hypothesis. And the next section here, we will go through some case studies trying to explain why this is important and why it's complicated. Because this is not only a theoretical discussion, correlation and causation are very, very often problematic and confusing in real life. So in the next video, we'll do some case studies about correlation and causation.